Traditional isolation mechanisms, like virtual memory and process boundaries, rely on privileged kernel operations to function. To create a secure container or separate process, a program must ask the operating system for root-level permissions to manage memory and hardware access. This reliance on the host OS creates two major friction points. First, security configurations aren't portable. A Linux setup won't simply run on Windows. Second, it creates an administrative bottleneck, requiring specific system-level tweaks and user ID management to run a single piece of code. These hurdles are particularly problematic for host processes like web browsers. These applications are designed to be nimble, rapidly downloading and executing untrusted network code without requiring a full system reboot or user permission changes. The engineering challenge is to isolate this third-party code inside the host process's own memory space, achieving security without the overhead or the permission of the underlying operating system. Software fault isolation, or SFI, solves this by moving the security boundary into the software itself. It ensures that untrusted code stays within its assigned limits by verifying its behavior at the instruction level. By enforcing these boundaries in user space, developers can bypass the portability and configuration issues that make a less-level security so rigid. WebAssembly, or WASM, is the most prominent vehicle for modern SFI. It's a portable bytecode format designed to be a fast, secure compilation target for high-level languages like C, C++, and Rust. Despite its name, WebAssembly does not achieve safety by trapping code inside a simulated virtual machine loop. An interpreter that checks every instruction as it executes is far too slow for native performance applications. Instead, a WASL runtime uses a just-in-time compiler to translate that bytecode into raw machine code. This allows the code to run directly on the host CPU at near-native speeds. This creates a high-stakes security tension. If the untrusted code is running directly on the hardware within the host's memory, we need a mechanism that physically prevents it from reading the host's private data. SFI resolves this tension by passing the code through a compiler that effectively strips it of its ability to address any memory outside of a specific, narrow sandbox. In a traditional C program, the heap, stack, and executable code coexist in a single address space. Without hardware protection, there is nothing to stop these layers from bleeding into one another. This unified layout is what makes stack-smashing exploits possible. A simple out-of-bounds write in the heap can reach upward to overwrite local variables or return addresses in the stack, leading to memory corruption. WebAssembly eliminates this through a disjoint state architecture. It physically separates the globals, locals, stack values, and heap into distinct, non-contiguous structures. Because the WASM heap is treated as a standalone array, an overflow can only reach the end of that specific array. Since the other states are stored in separate memory structures, the overflow hits a hard limit and causes the module to trap. Furthermore, the executable code itself is stored in a location the heap cannot address, preventing an attacker from injecting and executing their own shellcode. By architecting these memory states to be disjoint from the start, the compiler neutralizes entire categories of exploits before the program even begins to run. To maintain high performance, WebAssembly relies on static verification. Every module must declare exactly how many global and local variables it will use before the runtime ever executes a single instruction. The compiler uses these declarations to vet the code. If an instruction attempts to access a variable index that doesn't exist in those declarations, the compilation fails immediately. This upfront verification provides a major speed advantage. Since the compiler already knows every variable access is within bounds, it doesn't need to add any checking instructions to the final x86 machine code. The same principle applies to the stack. WASM bytecode is designed so that the compiler can calculate the exact depth of the stack at every single instruction in the program. For control flow branches, like an if-else statement, the validator requires that both paths result in the exact same stack depth before they merge. If they don't match, the code is considered malformed and won't run. This predictability allows the JIT compiler to generate native stack pointer offsets that are guaranteed to be safe. The untrusted code has no way to manually manipulate the stack pointer to point to forbidden memory. By validating memory and stack usage before execution, WebAssembly shifts the burden of security to the compiler, allowing the CPU to run the resulting code at full speed. Not every check can be performed statically. For example, a heap store instruction often targets a memory address that is only calculated while the program is running. In these cases, the compiler uses runtime instrumentation. It injects a safety check into the generated machine code that verifies the dynamic address is within the heap's size before the store is allowed to proceed. However, adding an if check before every single memory write would drastically slow down the program. To optimize this, the compiler uses block-level hoisting. In WebAssembly, instructions are organized into blocks that always execute sequentially from top to bottom. If a block contains several writes, the compiler calculates the total memory needed for all of them and hoists a single cumulative check to the very beginning of that block. If that one hoisted check passes, the CPU can execute the entire sequence of memory writes without any further interruptions, maintaining maximum hardware performance. This strategy is the hallmark of efficient SFI. It performs a small amount of upfront work to enable long stretches of unhindered execution. The final vulnerability is indirect control flow. In languages like C, function pointers allow a program to jump to an arbitrary address in memory, which an attacker can exploit to hijack the program's execution. WebAssembly neutralizes this with the call indirect instruction, which completely forbids jumps to raw memory addresses. Instead of using memory addresses, WASM uses a function table. This is a separate, validated array that contains only the starting points of pre-approved, safely instrumented functions. When the code makes an indirect call, the runtime simply verifies that the table index is within bounds. This makes it physically impossible for the program to jump into the middle of a function or into malicious data. Even if an attacker manages to corrupt an index value, the CPU can only jump to a valid, verified function within the table. The hardware is physically constrained from exiting the sandbox. Building a JET compiler that consistently outputs perfectly instrumented machine code is difficult and leaves little room for error. A framework called RWASM provides an alternative strategy for ahead-of-time compilation. Instead of generating assembly directly, RWASM translates WebAssembly bytecode into safe Rust source code. This is effective because the Rust compiler is already built to enforce strict memory safety and array bounds. By converting to Rust, the project inherits all of those safety guarantees automatically. By leveraging an existing secure compiler to handle the bounds checking, developers can implement software fault isolation with much less engineering complexity. In the final execution pipeline, the code clears its hoisted checks and runs on the hardware with minimal overhead. If an exploit attempt triggers an out-of-bounds error, it only affects the isolated memory of the WASM module. The runtime catches the violation and shuts down the module cleanly. Crucially, throughout the entire execution and even during a crash, the host process and the operating system remain entirely unaware of the attempt and completely uncompromised. By encoding safety rules directly into compiled instructions, WebAssembly achieves high-performance isolation without needing to trust the code or the environment.